So we'll first go through the outline to get a glimpse of all the different topics we'll be covering today, then go through each of those topics in more detail. So coming to the outline, let's first start with a basic introduction to the concepts of electromagnetic compatibility and electromagnetic interference. Then we will look into the Altair solution addressing these issues. Altair solution involves combining the field and cable simulations as well as combining the field and circuit simulations. So we will cover these two concepts in more detail. Then we will look into the automotive EMC issues where we will show examples of radiated and conducted emission analysis as per the EMC test standards. The automotive examples will be followed by the aerospace examples. More specifically, we will look into the lightning as well as electromagnetic pulse analysis examples. And before closing out, we can look into the student resources available from Altair side. And I would encourage or recommend everyone to post your questions in the chat without waiting till the end. At least during the previous webinars, Dr. Reddy was answering those questions as they come in. But at the end, I will also try to answer a few questions.
Gopi, one comment from the chat is that there's a banner on the top that's showing up as a black line. And for now, it doesn't seem to be that much of an issue, but maybe later, I guess I know what the banner is. But that's okay, go ahead. Maybe that's a Zoom banner, I guess, showing up there.
Maybe not ready.
Okay, go
So,
ahead.
yeah, from my side, I can't see anything except the screen I'm sharing. So, yeah.
Sure.
So coming to the concept of electromagnetic compatibility, it is nothing but the ability of a device to function without any errors in its intended electromagnetic environment. For example, if a device involves cables, and if those cables are not well shielded, or let's say if those cables are used at a higher frequency than their intended operating frequency, then they can receive external fields and introduce voltage or current disturbances in the device that they are connected to. So this is an irradiation scenario where the cable is not radiating but receiving external energy. Next is the concept of electromagnetic interference. Okay, so this can be explained as the electromagnetic radiation from a device interfering with the normal operation of the device or devices. Once again, taking the example of cables, and if those cables do not have enough shielding, they can radiate and couple into other cables or devices. So here we are using the example of a cable, but the same principle applies to, let's say, PCB traces or bus bars in a battery pack and so on. The cable analysis solution in Feko, it's applicable for both the radiation as well as the irradiation scenarios. Of course, one can use that for the combined scenarios, taking like a radiation scenario, taking irradiation into account. Okay. In general, the terms EMC and EMI are used interchangeably. So from here on, whenever we talk, we'll just use the word EMC, but inherently we mean both EMC and EMI. Okay. Now, coming to the Feko capabilities for EMC, EMI. So let's look into those capabilities before we look into the specific examples. Okay. But before jumping into the capabilities, I just have one slide about Feko, basically to introduce the software for those who did not attend the previous webinars. Simply put, Altair Feko is nothing but it's a 3D electromagnetic analysis software suite that offers multiple frequency and time domain solvers with the true hybridization. And because all those solvers are available within a single tool, it can be used for a wide range of problems, ranging from simple to extremely complex and electrically small to electrically large problems. And to list some of the popular applications, Feko can be used for antenna design, antenna placement, electromagnetic compatibility, which is the core topic of this webinar, and other applications like microwave components, RFID, bioelectromagnetics, and many more. Now coming to the Feko capabilities for EMC, it can be used for a wide range of EMC applications, including shielding effectiveness analysis, immunity, as well as radiated emission analysis. It can be used for noise coupling analysis as well. Radiation hazard analysis is another popular application. It can be used for lightning as well as the effect of EMP that can be analyzed in Feko as well. Feko can also be used for HERF analysis, high intensity radiated fields analysis. And in addition to all these EMC applications, Feko can also be used for designing EMC chambers, okay, both the reverberation as well as anechoic chambers. Yeah. So when you install the software Feko, it comes with a huge component library, which is a library of pre-designed antennas and platforms. And under this library, there are several EMC antennas as well as some EMC test setup models. So let's go through that library. So let me open the interface. So whenever you open the interface, you have the component library. And when you open the library, you can see a long list of pre-designed antennas and some platforms. And if you search with some keywords, for example, if I say EMC, then all the related ones to EMC are listed here. So you can see there are a few antennas, biconical, bilog, as well as a EMC horn antenna. And there is a log periodic antenna. And there are these test setup models as well, EMC test setup. So if you take any of these antennas, let's say you take the biconical antenna, so you can see like a typical performance that you can expect out of this antenna. And if you click on create model, it will be automatically created. And you can save it anywhere. Demo. I just want to show you like when you add an antenna to the existing design, how does it look like? So this is a Seniors antenna. We want to actually take a platform. Let me first add a platform. For example, a car. And then maybe we can add the antenna. Now, if I zoom to selection, now you can see the antenna. And these antennas, they are like fully designed and fully parametric antennas. So you can tweak these design variables if you want to fine tune the design for your design specifications. And you can even set up optimization and optimize this antenna if, let's say, the initial design is not meeting the exact specifications, or you want to use it or adjust the frequency of operation. So one can always take advantage of all the different antennas and platforms available under the Feko component library. Now, coming back to the different EMC applications, the next application we can look into is the shielding effectiveness analysis. Yeah. When it comes to shielding effectiveness analysis of enclosures, one can perform such analysis in Feko for the metallic enclosures as well as the dielectric enclosures. So you can see like what would be the effect of different openings in the enclosure, as well as the thickness of the enclosure itself, whether it is improving the shielding or making it worse. Okay, so let's look into once again an example to understand like how the setup would be done for shielding effectiveness analysis and what are the results one can plot for such an application. So here, this is an enclosure with some openings. So typically these would be openings, maybe either, let's say this is an enclosure for a PCB, and here you need to have an opening for the connector. So you can take those into account if there is some external radiation and the fields can penetrate through the openings, as well as if the thickness is less than the skin depth, then also the incident field can penetrate through the enclosure. So you can see how well the shield is protecting the device inside it. The way you set up such a model in Feko is just to mimic external incident field. You can use a plane wave, and you can request for fields inside the enclosure. In a separate model where you don't have anything but with just the plane wave, you can again compute the fields at the exact same location to see like what would be the incident field when you don't have anything. And then in a model like this with the enclosure, you can compute the fields inside the enclosure. Okay. Now, when you have such a model, you can plot the fields with and without the enclosure at the same location and take the ratio of those two fields. So here you can see I'm taking the ratio of the incident E field as well as the field inside the enclosure, and just taking the -20 log to convert that into dB. So this way you can plot the shielding factor. So the red curve, this is the completely shielded enclosure, but the blue curve, when there are some openings to account for the connectors and everything, you can see at the resonant frequencies, depending on the dimensions of the enclosure, at certain frequencies, enclosure can be of a resonant length. So that's why you see these peaks. At least close to those peaks, you see the openings has an impact, and that's why you see this difference between having the openings and not having the openings. The same thing can be done by changing the thickness of the enclosure as well. Okay? So the red curve is for an enclosure which is thick, and the blue curve is for an enclosure where the thickness is reduced. Obviously, when you reduce the thickness of the enclosure, the shielding was reduced. So with a thick enclosure, it was providing better shielding. So this way, one can easily perform the shielding effectiveness analysis in Feko for any of the enclosures. They can be either metallic or they can be dielectric. So here, this is a metallic enclosure. The metal is silver. So in Feko, you can define all different types of materials. So when it comes to materials, They can be dielectric metals, layered dielectrics, anisotropic materials. Okay, every sort of material is supported in Feko. The next EMC application was radiated as well as the susceptibility analysis, and those type of problems can be addressed by combining the field and cable simulation in Feko. Okay? Especially when it comes to the radiated emissions solution. It is a two-step process where you first solve the external problem. So because of the external incident field, and let's say if these applications are involving cables, so because of the external incident field onto the cables, you compute the fields on the surface of the cable, and using the transfer impedance and admittance, those fields will be converted into the sources for the internal cable problem. And the internal cable problem will be solved using the multi-conductor transmission line theory. Okay? If it is the opposite, then once again, it's a two-step process where, let's say you are driving a signal through the cable and you want to see the leakage from the cables. Then you first solve the cable problem using MTL and solve for the surface currents on the cable as well as voltage across the terminals. And then once again, using the transfer impedance and admittances, so you can convert those into equivalent sources on the surface of the cable. And using those equivalent sources, you can solve the external field problem. Okay? So to compute the fields at any desired location to see what would be the leakage from the cables. And when I'm describing this two-step process, please note that this is something that happens in the background, but when you are setting up, we'll just set up a single model with the 3D geometry as well as the cables included in a single project and run it once. And Feko will automatically do this two-step process in the background and compute whatever is requested as the desired output. So for these kind of problems involving cables, there is a fully integrated cable analysis module in Feko. So let's go through the options available under this cable analysis module. Once again, I will try to explain this using the interface. Okay. So in Feko, it is possible to model different types of cables with the different cross sections. So they can be either single conductor cables, coaxial cables, ribbon cables, or twisted pairs. So not only modeling these individual cables, so you can make a bundle of different types of cables, and those bundles can be shielded as well. And when it comes to shields, they can be single shields or double shields. For double layered shields, you can define both the inner and outer. And the shields, they can be solid tubular shield or they can be braided shields, where you can define the weave angle, the number of filaments in the weave, and the number of carriers to make the entire braid. Okay, so all those different parameters can be specified for the braided shield. Okay? If you don't have these parameters, then if you just have the transfer impedance or admittance properties of a shield, then you can import those properties also to define the shield. Not only having all these options for different cables, bundles, and the shields, once you set up a cable analysis problem in Feko, so typically you can add different types of terminations on the cable terminals in the cable schematic. So you can see here, you can terminate the cables with different RLC loads or complex impedances or transformers or like voltage controlled voltage sources. Even you can add some spice circuit models if you want to add some external circuitry where these cables are connected to. Or if you just have the network parameters, S parameters, Z parameters, or Y parameters of that external circuit that is connected to the cables, then you can import the network parameters as a general network and then connect that to the cable terminals. And along the length of the cables, you can add voltage proofs and current proofs as well at any desired location to compute the voltage across or the current through. So what you see here, this is a typical automotive harness where you'll have cable bundles that are split into different cables. So you can see from this point A to M1. So this is a bundle of two twisted pairs as well as a single conductor cable. And at this point M1, that is split into three cables. So there is a twisted pair from M1 to B. There is another twisted pair from M1 to C, and the single conductor is from M1 to D. Okay, so Feko do support the splitting of the bundles. Okay, and then which is typical for the automotive cable harness. Okay? The way a cable analysis problem would be set up in Feko is you first typically define the cable paths, and then you define the cable cross sections as well as the cross section of all the different bundles, and then you add the cable harness. When you add the cable harness, that is where you add the cable instances to say which cable runs along which path, and then you add cable connectors depending on the number of conductors in each path, and in the schematic you add all the different terminations. Hope that clarifies everything. Now, moving on further, the next capability that comes in handy for solving EMC issues is the combination of circuit analysis with field simulations. With this solution, it is possible to model the entire system as a combination of sub-circuits and perform the conductor emission analysis. In this process, cables can be included through their S parameters. When you compute the S parameters in Feko, they can be imported into another Altair tool, which is called Altair Activate. So this particular workflow involves a seamless interface between Altair Activate and Feko. Because I'm just introducing Activate, once again, I have only one slide. I don't want to spend too much time introducing the software itself. About Activate, it is nothing but a flexible tool for rapidly modeling and simulating products as multidisciplinary systems in the form of 1D models expressed as signal-based or physical block diagrams. Optionally, these are coupled to 3D models. It activates intuitive block diagram environment. It empowers users to rapidly build demonstrations of how real-world systems function and easily try new ideas without any need to build the prototypes. And the open integration platform of Activate allows modeling of any multidisciplinary systems with various domains such as mechanical or electrical or thermal or even control systems. And Hyperspace is integrated into Activate, which is a very fast and accurate spice solver. In fact, the same spice solver is integrated into Feko as well. Okay? So for EM applications, Activate supports both the transient as well as AC analysis, and it has, as I said before, a seamless interface with Feko for exchange of data. So now that we looked into the cable and field coupling solution as well as the circuit and field coupling solution, let's look into a few use cases where this combined solution can be used to solve some automotive EMC applications. Okay? So before that, let's first go through the automotive EMC development process. Okay? Of course, this may not be limited to automotive. It can be the same process for other industries as well. But here, just I'm taking the example of automotive. Okay. So, in general, identifying issues during the design process itself, it would definitely help in reducing the overall design life cycle. Okay, and this is where the simulations comes in handy, because you don't need to rebuild the prototype and do a testing every time. Okay? So using simulations, one can address the key EMC issues at a component level as well as vehicle level during the design and validation process, and perform measurements on the final hardware prototypes. So the simulations will definitely help in pre-validation before hardware prototypes are available. And simulations will also help in analyzing and understanding the issues during these validation tests. And understanding of the issues will help to improve the designs and create new design guidelines and processes. It is also possible to better understand the correlation between the component and the vehicle tests. It is also easy to manage the complexity of different vehicle variants in a CAE environment rather than building a prototype for every variant. So this can definitely help in reducing the prototypes. Now, before looking into any specific examples, let's go through the key EMC use cases that can be addressed with the simulations. Okay. So simulation of EMC tests, both emissions and immunity, according to EMC standards at vehicle level, they are supported. And prediction of radiated emissions on hybrid as well as electric vehicles, including even the high voltage cables, that is also supported. Emissions from Ethernet cables coupled into other devices or antennas. RF noise coupled into automotive antennas like the AM or FM or the DAB antennas. You can optimize cable routing to eliminate key, like some dead zones for the key fob. And you can do the crosstalk analysis between the sensor cables as well as the wiper motor cable. The radiation exposure to passengers as per the IC and IRP standard for antennas and high voltage cables in vehicles, so that can be performed using simulations. Conducted emission analysis in DC to DC and DC to AC converters through circuit simulation. EMC issues due to wireless power charging, for example, in systems like remote keyless entry. As composite materials are used to reduce car weight these days, we can analyze the shielding effectiveness of these materials as well. And it's also possible to optimize the shielding enclosures for different electrical devices. And many more EMC use cases can be addressed through simulations. Now, let's look into an example of EMC analysis of an electric vehicle powertrain as per the CISPR 25 regulations. Okay? So this would give a complete understanding of how the combined field and cable as well as the field and circuit simulations would come in handy for solving these EMC use cases as per some EMC standards. So this analysis, when it comes to this powertrain, will help in improving the electric vehicle powertrain design in the early stages of the development process. Okay? And the work that we are presenting here, this was done in collaboration with the EMC group at the Polytechnic University of Milan. So here you can see a powertrain design of an electric vehicle, which includes a battery, line impedance stabilization network or list, DC, as well as the three-phase AC cables. There is an inverter and a motor. In a simulation environment, we can come up with the circuit models of all the powertrain components, including the high-frequency parasitic effects, which are typically important for EMC. It is also possible to perform tolerance analysis, and design optimization using the fast circuit simulations. The circuit model can be an accurate representation of this is for 25 test setup, and this will further help in understanding the design behavior, the component level, as well as the vehicle level. And the knowledge we gain from the simulations can be used to provide recommendations on installation and integration in the entire vehicle. Now, when it comes to the Altair solution, which is a combination of circuit cable and field simulation, so there are three different stages of the solution. The first is the component level using the circuit simulations. The second is the sub-assembly level. Here we emulate the measurement bench setup in a cable and field simulation environment. And finally, at a vehicle level, where the CISPR25 setup is transferred into the vehicle. Yeah? So once again, we can use the cable and field simulation solution here. And for this entire process, as I said before, this is possible because of the seamless integration between Activate and Feko. So let's first look into the circuit simulation at the component level. So here you can see the circuit models of all the powertrain components modeled in Activate. The DC and three-phase AC cables are included through their S parameters. So these S parameters are computed in Feko first for the cables. We can use the circuit models to obtain the signals which can be used as excitation in the 3D field simulation at the sub-assembly or the vehicle level. The circuit model is used to optimize the powertrain design, including the ground connection of the shields, length and routing of the DC and three-phase AC cables, the operating point of the motor drive system, and so on. So here you can see the equivalent circuits of the inverter and the motor. The circuit modeling supports not only the low frequency functional models, but also the high frequency parasitic components, which are important for EMC. The components shown in red here in the equivalent circuit, those are the parasitic components. And this shows the common and differential mode voltages at the output of the list. So this is what we need to measure as per the CISPR25 regulations. Okay? The cables in this model are shielded wires whose S parameters, as I said before, they are computed in Feko and brought into Activate. So this is the plot of the common and differential mode voltages measured at the output of the list. So what we are looking here is if the peaks are associated with the switching frequencies of the inverter and its harmonics. You can also see the difference between the common mode and the differential mode. Okay? So the blue one is the common mode and the green curve is the differential mode. As expected, the common mode is greater than the differential mode. Obviously, that's what people do to reduce the EMI issues. So people try to use the differential mode. Now that we looked into the circuit analysis, let's look into the combination of cable and field simulations at a component level. So this is the overview of the emulated CISPR25 test bin setup in Feko. So you can see that we have all the modules except the list. So instead, we have the monopole antenna. So we'll be measuring the load voltage at the monopole here. So here you can see the DC and AC cables modeled in Feko. Each wire model is based on coroplast shielded cable, so which is typically used in automotive electric powertrain. And these are the equivalent circuits of the battery, the inverter, and the motor. You can also see the low noise amplifier model connected to the monopole. So that was imported into Feko as a non-radiating networks using its network parameters. So just want to mention that Feko do not support active components directly. So that's why we are using the network parameters. So what we did is measure the output of the inverter in Activate and use that as an excitation to the cables in Feko. And you can see the individual plots of the three-phase voltages, including the equivalent circuit model in Feko. And the radiated emissions are measured at the load voltage on the monopole. So you can see the individual phase excitations as well as the combined results, adding the three phases. Now, let's look into the cable and field simulations at the vehicle level. The CISPR 25 bin setup is now transferred into the car. And here, we will look into the radiated emissions by varying the lengths of the cables. So once again, the output will be the load voltage at the monopole, which is located on the roof of the car. So here you can see two different configurations for different lengths of the AC and DC cables. The bottom configuration has cable lengths similar to the bench setup we saw previously. When it comes to the CISPR 25 regulations, the electric field limits are given for measurements performed with a CISPR 16 compliant EMI receiver. To emulate this test regulation, we transformed the output data as if it is equivalent to what is measured by a CISPR 16 EMI receiver. So this is done through a post-processing Lua script. When it comes to any automation in Feko, it can be done using Lua scripting. So it is integrated into both CAD Feko, which is the pre-processing environment, as well as post Feko, which is the post-processing environment. Basically, we transformed and combined load spectrum to a complex time signal. And in post Feko, it is possible to specify any desired time input once you do the simulations over a wide frequency range. Then split the time signal into overlapping partitions and apply Gaussian window function to each partition. Then do FFT on all the windowed partitions. For the peak detector to take the maximum spectral response over the partitions. For the RMS detector, we calculate the RMS spectral response value over the partitions and then store the peak and RMS frequency responses. Now looking at the results, the blue curve here represents the data from the bench setup, and the green curve represents the same cable length as the bench inside the car. Okay. And the red curve is for the modified cable length inside the car. Okay. So this way, one can always do analysis or simulations on a circuit level, at a sub-assembly level, as well as a full vehicle level, using a combined workflow between Activate and Feko. And just by adapting simulations, you can have many different variants of your test setup and look at the impact of your changes before or without relying on measurements for every variation. Now let's look into the automotive example, which is the radiation hazard analysis. So here we will look into the wirelessly charged hybrid or the electric vehicles. Okay. When it comes to wireless charging, whether it is for electric or hybrid vehicles, this is a topic being explored by many in the automotive field. So there are two approaches to wireless charging, either through magnetic resonance or through magnetic induction. And Feko can be used to design the coils and antennas and investigate the safety issues of these wireless charging systems. So here you can see the generic model of the wireless charging system built in Feko, which is similar to the ICS 115 that's on the left. And the coil in the ground module has 20 tons, which is the bigger one. And the core module coil has 15 tons, the one on the top, which is the smaller one. And these are the magnetic field lines between the ground module and the core module. And here you can see the efficiency plots of the core module coil at different frequencies for varying heights of the core module above the ground module, for different displacement and also for different displacement positions at a fixed height. So that's the advantage of simulation. So you can easily either just vary the height or vary the position and do a parametric sweep. So we can compute the radiated fields of the coils to evaluate the safety hazards as per the ICNIRP regulations as well. So here you can see the radiated fields and the presence of human phantom with and without the car. So these are the ICNIRP regulations specifying the maximum allowed B field limit and the E field inside human body. So you can see here the regulations are revised around 2010 with a higher limit for the radiation exposure. So in Feko, we can compute the radiation zones where the field level is more than the allowed limit as per the ICNIRP. So with a higher limit in the revised regulations, the hazard zone is much closer to the coils now, looking at the plots on the right. We can definitely consider human phantoms and evaluate the field levels inside the human bodies in a simulation environment. So here you can see three different positions of the human phantom with respect to the core and the coil. In a standing position, the fields in the legs are above the 1998 exposure limit, but below the 2010 limits. The same is observed in the sleeping position as well. So far, we looked into different automotive use cases. Now let's look into some aerospace examples. Okay? We'll first go through the lightning analysis example. So here you can see a generic aircraft fuselage with a cable inside. So there are two ways one can do a lightning analysis in Feko. So one is to model the lightning cage around the fuselage, and the other is by using the impressed current excitations in Feko. So here for this generic setup, which is just basically a cylindrical fuselage, you will use the cage model. So the cage is metallic, whereas the fuselage, it's a carbon composite with metallic end caps. You can see the cable routing as well inside the fuselage and the terminations on the cables in the schematic. So the cable that we used in this particular case, it's a coaxial cable. You can see the surface currents on the fuselage and the fields inside. As expected, the fields are stronger at higher frequencies. So here you can see the lightning pulse used in the simulation. So the lightning has a sharp rise time and a slow fall time, which is one of the standard time pulses available in Feko. You can also see the induced voltage across the cable terminals because of the lightning. So that was a generic cylindrical fuselage. So here, the next example is the case of a full aircraft So in this case, we use the induced current excitations at the strike point and exit points instead of the lightning cage. You can also see the two antennas and the cable inside the fuselage here. So in the plots, you can see the induced currents on the antenna ports as well as the cable terminations because of the lightning. So let me show that example. So this was that example where under the source flow tab, you have the impressed current source, which can be used for lightning analysis. So here, this is the lightning strike, and this was on the back, that's the exit point. And we added loads on both the antenna ports. And we also have a cable inside the fuselage. So we can also see like what is induced onto the cable because of the lightning. So if we go into post Feko, so this is the post Feko where we can plot the input time signal. So if I plot the input time signal, so you can see this is the lightning signal, the sharp rise and a slow fall. And if you look at the currents induced onto the antenna ports, so load one is the antenna on the top, and load 2 is the antenna on the bottom. And these are the currents on the loads and the cables. So when we add cables, if I go back to the Feko model, so when you add any terminations onto the cable terminals, you can request for the probe voltage and probe currents. This will help to plot the current through or the voltage across these loads and plotting the results. And that is what we did here using those probe currents and voltages. So this way, using the simulations, you can always set up a lightning analysis and see like the effect of lightning on either the antenna components or the different cables inside an aircraft. Now, the next one would be the electromagnetic pulse investigation. It is important to investigate the effect of EMP to understand how the electronics inside the aircraft might be affected when hit by a strong EMP. And for this purpose, we selected a Learjet model, which includes the windows and some internal cables. The EMP incident field is generated with a plane wave excitation and Feko. The EMP waveform and the corresponding spectrum chosen for this study is based on the values we found in the literature. So you can see on the left is the time plot, and on the right is the frequency spectrum plot. And here you can see the 3 different evaluation points, which are the positions for cockpit controls, the audio visual system mount, and the engine inlet. So from the field data at these 3 points, you can clearly see that the cockpit section is most severely impacted by the EMP. And looking at the voltages and the currents induced into the cables, you can see that the measured voltages and currents at the 2 cable terminals are same in magnitude. However, the phase is different because of the delay along the length of the cable. So as I mentioned before closing out the webinar, I would like to go over some of the useful resources that are provided by Altair, especially for students. First and foremost, the fully featured Feko software is available to all the students for free. I would definitely recommend all the students to take advantage of it. Along with the free software, there are several e-learning modules available on Altair website. So to learn the software, you can definitely go through these e-learning modules. So when you complete these modules, I think you can receive a certificate as well if you're interested to receive a certificate. And if you run into any issues while exploring the software, or let's say when you're working on any project, you can definitely receive help through Altair community. The community, it's a great place to interact with other users, to help or to receive help, or even help other users when they post questions, or even to have some technical discussions around different topics. Last but not least, I would recommend this book that is co-authored by Dr. C.G. Reddy. I don't think he requires any introduction here, but so the examples in this book, they are done using Feko. So you can definitely learn different antennas using the book, but you can design those antennas using the Feko software, run and look at different results to see how those antennas are performing. So thank you all for joining today.